Am I audible and visible? Good evening, my dear students. And good evening, my dear students, and welcome to this session. How many students are there? Okay, so am I audible and visible to you? Anything you would like to ask? So today we are going to start with the ideal gas law. We have already done the individual laws. We have done the Boyle's law, we have done the Charles law, we have done the Avogadro's law, we have done the Gay-Lussac's law. So today we are going to start with the ideal gas law, and once we have done the ideal gas law, we are going to do the Dalton's law, the Graham's law of diffusion, and I hope today you will be able to understand these laws perfectly. And these laws are extremely important because they are going to be asked in your NEET examination, and these laws are responsible and they are required for the chapters like thermodynamics, like equilibrium. There also you will need these laws. Now, why am I getting one waiting? Why am I not getting how many students have joined? Okay, so we have got 6 watching. Great. I'm perfectly fine, Teethraj, Ritik, Ananya. So all of you are here. Like, subscribe, share and comment on this particular video. So let's begin over with it. And I hope you already remember what about my credentials. I'm an MSc in chemistry from University of Delhi. 26 plus years teaching experience and lakhs of students have been taught by me. So to begin over with it, let's talk about the various laws. Now we have various laws. We have Boyle's law, we have Charles' law, we have Gay-Lussac's law, and we have Avogadro's law. And to talk about these, now let me write. I'm gonna start writing. Anybody has to ask anything, and you need to comment and you need to like the session. We have the relation with volume. We have the relation with volume. We are going to talk about volume. So volume is proportional to 1 by P. Now that's Boyle's law. Okay, at a constant temperature and the mass. Amount remains the constant, the temperature remains the constant. Then we have V is proportional to temperature in Kelvin. That's Charles' law. Again at the constant pressure and amount. Then we have V is proportional to N. N is the number of moles, or you may say it to be the amount. So here we have V proportional to N, that is amount, and that's Avogadro's law. Clear? Prerna, we are going to start the classes in app from next week. Next week onwards, we are going to start the classes in the app itself. So this is what we have as the Avogadro's law. Now you need to understand a very simple concept, very simple concept. If any quantity depends on multiple independent quantities, remember, if a quantity depends on multiple independent quantities, then that quantity also depends on their multiplication, their product. So it would mean that this V, which is proportional to 1 by P, which is proportional to temperature, and which is proportional to number of moles, this is going to depend on their product as well. So here I can simply say that V is proportional to NT by P. Is this clear? And now since I have used the amount also, I have used the temperature also, I have to use the pressure also, and I have the volume also, I don't need to give any condition. This particular relation is unconditional. It could be at any temperature, it could be at any pressure, and it could be at any volume, it could be at for any amount. So here we do not have any kind of condition. Clear? So here it would be quite logical that I place a constant. All the other constants are going to be conditional, but this constant which I am going to place is going to be universal. Universal constants are those which do not depend on the condition, rather they depend on just the dimensions. That is, the dimension, like the measurement system that I use, that is going to decide the value of this particular constant. The universal constants are constant irrespective of the condition, but they depend on the system of measurement. So here this constant has been termed as R. So I get the value as V is equal to R NT by P, where this R is what we call as the universal gas constant. R is the universal gas constant. Whatever is written on the board at this moment, you need to remember it and you need to copy it down. Any confusions here, anybody? So this is an extremely important part. So this is what we have as the universal gas constant. Copied it down? Anyone has to ask anything in that? So here this is what we have as universal gas constant. And now we have got V is equal to nRT by P. So this can be just twisted around. R, the universal gas constant, would be equal to PV by NT. The units of this R are going to depend on the units of pressure, units of volume, units of amount, and units of temperature. Now, temperature unit are always Kelvin. We are not going to use the degree Celsius or Fahrenheit as a unit. We are going to use only the Kelvin as a unit, because the proportionality is for the absolute temperature. It is not with the temperature in degree Celsius or degree Fahrenheit. So we are going to use the temperature as Kelvin only. The amount, again the universal unit of amount is going to be moles. Please understand, we can even use the unit as molecule. In that case, it's known as the Boltzmann constant. Boltzmann constant is the gas constant per molecule. Otherwise, we have the gas constant, so the amount is going to be mole. But the pressure and the volume could be having different units. Like pressure could be having a unit of atmosphere, it could be having a unit of bar. But these are the two main units that we talk about, or we can have the pressure unit as Pascal if we are going to talk about in the SI units. Similarly, when we talk about the volume, volume could be in decimeter cube, that's same as the liter, or it could be in meter cube, that is the SI unit. So let us see what are the values of these gas constant once we change the units. So this R, and please remember the gas constant has been determined experimentally. It is not predicted but determined experimentally. So when we talk about this R is equal to, if we take the pressure in atmosphere, the volume in liters, the amount in mole, and the temperature in Kelvin, the value comes out to be 0.0821. 0.0821 atmosphere, liter, mole inverse, Kelvin inverse. Clear? If I take the dimensions to be bar, the volume in decimeter cube, or you can say it liter. Liter and decimeter cube are one and the same thing. Per mole and Kelvin, then this value comes out to be 0.0831. Remember, the bar is slightly lower as compared to atmosphere, and that is why the gas constant is slightly higher when we talk about bar. Clear? And if I use it to be Pascal and meter cube, please remember 1 Pascal has the dimension of Newton per meter square. Clear? So when we multiply the Pascal into meter cube, it becomes equal to Newton per meter square into meter cube, that is equal to Newton meter, which is equal to joules. Is this clear? So when we talk about, it comes out to be 8.31 joules mole inverse Kelvin inverse. Now once we have got the value in joules, we can easily convert joules into calories by dividing by 4.186, because 1 calorie is equivalent to 4.186 joules. So if I use the calories, this R value comes out to be 1.987 calories mole inverse Kelvin inverse, which is most usually approximated to 2 calories mole inverse Kelvin inverse. If I don't have to deal with the various dimensions and I have to use the answer in the most easy way, most often we take the value of R to be 2, that is in calories. So this is what we have as the values of the gas constant R. Note it down, this is a very important concept. Sometimes R is approximated to 25 by 3, 8.31 joule, this is 25 by 3, something approximately 25 by 3. In fact, 25 by 3 is slightly higher than this value. Calculation and all. Is that clear? Okay. Now we are going to use the modification of the ideal gas law. So this is what we have as V is proportional to NT by P, V is equal to NT by P, this is the universal gas constant, and the ideal gas equation is PV is equal to nRT. Okay. Now to get a little further in that, we have the equation as R is equal to PV by NT. Okay. We can twist it around, we can get it as PV is equal to nRT. Okay. Now, should I not write it like this? Okay. We are going to write it as R is equal to PV by NT. So we can write it as PV is equal to nRT. Okay. Now here, what we can do is, since PV by NT is equal to a constant, what I can say is R is equal to P1 V1 by N1 T1 will be equal to P2 V2 by N2 T2. So if we have to compare two different systems and we need to get the value of one thing from the other thing, then in that case this can be used as the equation, or for the transformation taking place in the single system, this is the equation that we can use. Further, here obviously we have PV is equal to nRT, but what we can know is that this N is equal to number of moles. Number of moles can be written as mass divided by molar mass. So N is equal to mass divided by molar mass. So N can be written as the mass of the substance, let us use the word alphabet W for that, and the molar mass we use capital M for that. I prefer not to use the small m and capital M because small and capital M of most of the students, they appear to be identical. So that is why I'm writing W and M, where W stands for the mass of the substance or the gas in this case, and M is the molar mass of the gas. So here we can always write it as PV is equal to W by capital M RT. And you need to understand that weight and mass in chemistry are one and the same thing. So here, rather than using the mass, I can use weight. Clear? A little twist it around and we get PVM is equal to WRT. Or here, if you mention it, it becomes R is equal to P1 V1 capital M1 divided by W1 T1, and that's equal to P2 V2 M2 divided by W2 T2. Fine. A little twist here and you get PM is equal to W by VRT. Now what is this W by V? This is mass by volume. When we talk about mass by volume, that becomes equal to density. Now what symbol you are going to use for density, it's your wish, but the preferable is you use the simple symbol as D, or you can use rho, or you can use sigma, whatever you wish to use the symbol as, it's up to you. I am going to use the simple symbol, that is D. So here I am getting PM is equal to DRT. So here is the relation of the ideal gas equation with density. Any kind of confusions here? So here also what I can do is I can say it is R is equal to volume by mass. It is 1 by density. So it becomes P1 M1 by D1 T1 is equal to P2 M2 by D2 T2. Just remember, there are certain equations written on the board at this moment. From this time onwards, this instant onwards, you are not going to use any other equation. You are going to use only the ideal gas law and only the equation given by ideal gas law. You are not going to use Charles' law, you are not going to use Boyle's law, you are not going to use Avogadro's law. You are just going to use the ideal gas law for any calculation regarding the gaseous state. What maximum can happen? There are going to be certain quantities which are going to be common. So if we have the constant volume, then in that case, you can simply put both the sides V as V. It's going to get cancelled out. If you have constant pressure, then you can put it as P, it is going to get cancelled out. If you have constant mass, you can put it as M and it's going to get cancelled out. So don't even think of using Charles' law, Avogadro's law, Boyle's law, whichever law you might have learned separately. Just use the ideal gas law and get the answer accordingly. Is this clear? Anything you want to ask here? So that is what we have as the ideal gas law. This is what we have as the equation. Whoever is watching, I believe you have copied it down. Clear? We can have so many questions regarding this particular concept. So this is the ideal gas equation in terms of density, which we have already done. Is this clear? If the mercury in the barometer is replaced by water, what will be the resulting height of the water column? Density of mercury is 313,600 kilogram per meter cube. Near about 14 times that of water. At a normal temperature or normal pressure, it is 76 centimeter. and we have to give it in meters. So it is going to be 0.76 meter. Simply speaking, when we talk about the density of water, that's 1000 kilogram per meter cube. Mercury's density is 13600 kilogram per meter cube. So density of mercury is actually 13.6 times the density of water. So the height of water is going to be 13600 divided by 1000 meter. I believe you already understand this, that why we don't use water in the barometer. Because if we are going to use water in the barometer, the height is going to be, it is going to be 0.76 multiplied by 13.6 meter. Calculate it out, and what value does it come out to be? Okay. So, got the answer? So here we have, okay, you got that answer, 10.336. Clear? Okay. Now we are going to get along with something called the Dalton's law of partial pressure. Before we get along with Dalton's law of partial pressure, let us understand what is the meaning of the word partial pressure. Okay. So to talk about the word partial pressure. Partial pressure is the pressure which is exerted by a gas in a mixture of gases as if it is the only gas in the mixture. It simply means that the pressure exerted by the gas is not dependent on how many gases are present in the mixture. Every gas exerts its own individual pressure. It is something like, let us say we have so many students writing an exam in an examination hall. It actually does not matter how many students are there in the examination hall. Each student is going to write his own examination paper, and number of the answers given by a student is independent of the fact whether it happens to be a single student or there are multiple students in the examination hall. In the same manner, the pressure exerted by the gas is the same irrespective of the number of gases in the system. Clear? So, that is what we call as partial pressure. So, partial pressure is the pressure exerted by a gas in a mixture of gases. This is what we call as partial pressure, and it is independent of the number of gases in the mixture. It is exactly the same. Now, Dalton's law of partial pressure simply says that whenever we have a mixture of unreactive ideal gases, so Dalton's law of partial pressure is valid for non-reacting ideal gases, the gases which do not react with each other. So, for non-reacting ideal gases, the total pressure exerted by the mixture is equal to partial pressure of the first gas plus partial pressure of the second gas plus partial pressure of the third gas, and so on. So, what we get is that total pressure is actually summation of the partial pressure of individual gases, summation Pi. Pi is, I is a variable, we can have multiple gases out here. What is aqueous tension? It's the vapor pressure of water at a given particular case. Clear? It's the vapor pressure of water at the given temperature. That is what we call as aqueous tension. So here, so this is what we have as Dalton's law of partial pressure. Now, one thing is, there is one very peculiar answer, very peculiar fact, that the partial pressure of any gas, Pi, will be equal to mole fraction of the gas into the total pressure, where this I is the mole fraction of the ith gas in the gaseous mixture. Is this clear? So, that is what we have as the mixture of non-reacting ideal gases. Remember, Dalton's law of partial pressure will not be valid for a mixture of NH3 with HCl, because the amount of NH3 and HCl that we have put into the reaction mixture is not going to be the amount of NH3 and HCl we are actually going to see, because NH3 and HCl are going to react with each other to form NH4Cl, which is going to be a solid. So, that is a peculiar confusion. So, these are the reactive gases. So, you need to understand that they might ask you which of these cases that Dalton's law of partial pressure is not valid. That is going to be the case where the gases react with each other. Okay. Now, could we have a small question? Calculate the partial pressure of each gas in a mixture containing equal masses of hydrogen, helium, methane and oxygen under a total pressure of 5.4 bar. Could you just give me the answer of this question? What you need to do in this question is, first of all, you have to find the mole fraction of each gas, and then you need to multiply that mole fraction by 5.4, and you are going to get the partial pressure of each gas in this mixture. Could you quickly do it? Solve the question. Solve the question. Partial pressure of hydrogen is going to be equal to, let's say mass of the gas is m. It's going to be m by 2 divided by m by 2 plus m by 4 plus m by 16 plus m by 32 multiplied by 5.4. That comes out to be 3.2 bar. When we get partial pressure of helium, that would come out to be 1.6 bar. If we have partial pressure of methane, that's going to be 0.4 bar. And we talk about the partial pressure of oxygen, that will turn out to be 0.2 bar. Ananya, the total pressure is 5.4 bar, and oxygen's pressure, how can it come out to be 5.25 bar? Hydrogen would be having the highest pressure here. Is this clear? So that is what we have as the Dalton's law of partial pressure. Clear? Now you need to remember the partial pressure of a gas is independent of other gases present in the non-reacting mixture. Is this clear? Vapor pressure is the pressure exerted by the vapor in equilibrium with a liquid at a given temperature. That is what we call as vapor pressure. Vapor pressure we have already discussed in the chapter called solutions. Clear? The vapor pressure is independent of the temperature. And this vapor pressure of water is called aqueous tension. Now, this is what is termed as aqueous tension. 821 milliliter nitrogen gas was collected over liquid water at 300 Kelvin and 1 atmosphere. Okay. If the vapor pressure of water is 30 torr, then the number of moles of nitrogen gas in the moist gas mixture is. Now you need to understand that if we have 1 atmosphere, 1 atm is 760 torr. So the total pressure is 760 torr. When we talk about the pressure of nitrogen, where that will be equal to the total pressure minus vapor pressure of water, that will be equal to 760 minus 30. So it is 730 torr. Now you can easily actually find out the volume, or I should say moles of nitrogen gas. We have PV is equal to nRT. So N is equal to PV upon RT. When we talk about the pressure, then in that case we get it as 730 divided by 760, that is in atmosphere. Volume we have 821. Entire gas occupies the entire volume of the container. Whatever be the gas, every gas is going to occupy the entire volume of the container. They don't compartmentalize. divided by R, that is 0.0821, and temperature is given as 300 Kelvin. So it is into 300. So when we cancel it out, it's 821 milliliter. So I need to convert it into liters. So here denominator again is going to have 1000 also with it. So if I divide it by 1000, it becomes 0.8. This becomes 10. So calculate it out. You will be able to get the answer. Any confusions? Now we get along with something called diffusion. Diffusion by definition is the net, spontaneous flow of particles from a region of their higher concentration or their higher partial pressure to a region of their lower concentration or lower partial pressure. So that is what we call as the diffusion. No, Ananya, today we don't have the class at 9 p.m. I feel that we are going to have the regular classes at 9 p.m. from tomorrow onwards. There would be special classes, there would be normal classes, so many classes. Okay. So we have the net spontaneous flow of gaseous molecules from a region of their higher concentration, that is higher partial pressure, to a region of their lower concentration, that is lower partial pressure. And what does it mean, net? Let us say we have a container with a partition in it. Now here we have the gas at a pressure P1, here we have the gas at a pressure P2, and here we create a hole. Please remember, the gas will move from a region of one pressure to a region of another pressure, and both the direction the gas is going to flow. But the gas is going to flow more from the region where it has a higher pressure. So the net movement will be from a region of higher pressure to the lower pressure, whereas the gas actually is flowing in both the directions. So the diffusion is not unidirectional. Diffusion is bidirectional. Diffusion is bidirectional. So the gas molecules are moving randomly in all the directions, but it so happens that whichever side the pressure is higher, the gas molecules move more from that side. So the net flow becomes from the higher pressure to the lower pressure. Is this clear? So that is what we have as the diffusion. Now once we have understood what is the diffusion, now we talk about the Graham's law of diffusion. Graham's law of diffusion is a simple observation which has a very logical reason. A gas which has a higher density at a specific temperature. We compare all the gases at the same temperature and pressure condition. Clear? Gas density is compared at a fixed temperature and pressure. So gas density is compared at a fixed temperature and pressure. Clear? Now when we compare the gas density at a fixed temperature and pressure, then the gas which has the highest density diffuses the slowest. Clear? Higher is the density, slower is the movement or the rate of diffusion. Clear? Now Graham observed that the rate of diffusion is inversely proportional to the square root of density. Rate of diffusion is inversely proportional to the square root of density at constant temperature and pressure. Is this clear? Now what we have observed is we have an equation, that is R is equal to Pm by dt. Is this clear? R is equal to Pm by dt. So d would be equal to RT by Pm. क्या कर रहा हूं मैं? What exactly I am doing? उल्टा. D is equal to Pm by RT. Okay? Yes, Ananya. Higher the density, lower is the rate of diffusion. So D is equal to Pm by RT. Now, if I substitute it right here, I get R is proportional to 1 by under root of Pm by RT. Is that clear? Now, here we have taken the temperature as a constant, pressure as a constant, and R in itself is a constant. So, why do I need to write R, P, R and T? These are the constants. We are going to include those constants in the constant of proportionality. So, this simply implies that R is proportional to 1 by under root of M, where M is the molar mass. Is that clear? So, M is the molar mass of the gas. Clear? Any confusions out here? Ananya, buffering, if it is taking place, that should be from your side. From my side, it is absolutely fine. Clear? So, this is what we have as the rate of diffusion. Now, once we have talked about this rate of diffusion, we can compare the rate of diffusion of various gases. So, it is mostly used as comparison. We have the various gases. We have R1 by R2. Now, when we are having the comparison of the rate of diffusion, then in that case, the constant of proportionality is going to get cancelled out. When the constant of proportionality gets cancelled out, it is going to become 1 by under root d1 divided by 1 by under root d2, which actually will turn out to be under root of d2 by d1. And that will turn out to be under root of molar mass of the second gas upon molar mass of the first gas. So, that is going to be the relation. And please remember, the rate of diffusion of both the gases must be measured at same temperature and pressure. There should not be different temperature and pressure. It should be the same temperature and pressure. Is that clear? So, that is the comparison. Okay. Now, the units of rate for comparison. When you compare the various gases, there are specific units of the rate. Please remember, the rate can be given in any units, but for comparison, we have certain specific unit. The rate unit could be mole time inverse, that is amount time inverse. It could be in volume time inverse. It could be in number time inverse, or it could be even in the distance traveled by the gas time inverse. Clear? But mass time inverse can be a unit, but cannot be used for comparison. I don't say that mass per unit time cannot be given to you, but if mass per unit time is given to you, then in that case it needs to be converted into any other factors. The mass per unit time cannot be exactly used. Is this clear? Any doubts, any confusions here? So that is what we have as Graham's law of diffusion, and that is how we are going to compare the various units. Now, one thing we need to understand that Graham's law of diffusion was not there in the last year's NCERT. That is, in 2022 NCERT 11th class, Graham's law of diffusion was not given. So we can safely consider that Graham's law of diffusion is not going to be asked in 2024 NEET examinations. Yes, I know that many of the teachers and every teacher, even including me, we are doing Graham's law of diffusion, but Graham's law of diffusion question has not been asked for the past 3 years. So there is a possibility it might not be asked in 2024 also, but still, since it is available in the previous year questions and now the entire chapter has been removed from NCERT, so nobody stops them from giving the questions of the previous NCERTs. So that is why we have done the Graham's law of diffusion. Is that clear? Now, in addition to diffusion, there is something called effusion also. Effusion is the gas escaping through a small orifice. And we have the Graham's law of diffusion and effusion. Under a similar condition of temperature and pressure, the rate of diffusion or effusion of gases inversely proportional to the square root of their densities. And density is the density measured at a constant temperature and pressure. Okay. So this is what we have as general form of Graham's law of diffusion. X milliliter of H2 gas effuses through a hole in a container in 5 seconds. The time taken for the effusion of the same volume of the gas specified below under the identical condition is. Hydrogen is the most easy diffusion because hydrogen has the lowest molar mass, and so its rate of diffusion would be the highest. All those who have not liked the session till now, go ahead and like it. So that's the end of the small session today. We are going to do the remaining portion of this chapter in the next class. At 3 p.m. every day we are having the biology session with Dr. SACHIN KAPUR, and the 4 p.m. is the chemistry session with me, that is Anoop Vashishtha. Join our Telegram channel for YouTube classes, that is PDFs and all. You are going to get the session PDF on this particular channel. Yesterday's PDF also are available on this channel, that is NEET Elixir by Unacademy. We have around 800 members as yet, 53 online. So these are the PPTs available here. This is the solution, this is surface chemistry colloid, this is human reproduction, and this is the today's PPT as well. Go ahead and join NEET UG subscriptions. You have Iconic, Plus and the Centers. Plus and the Centers, they include all things. Iconic, Plus and Centers, they include everything available on the Unacademy of a particular goal. Select your goal, Unacademy app, download the Unacademy app, install it and select your goal and join with using the code AVLIVE. You can follow me on my page, that is unacademy.com/Anoop Vashishtha. Follow it, go ahead and join with me. Subscribe to the NEET Elixir by Unacademy for the best live classes. Like, share and comment on this particular channel, and please share it with your friends. Thank you. We'll meet in the next class, that is tomorrow, evening 4 p.m. Till then, bye-bye, take care.